Okay, this video is for Lab 9. We're going to be going over malloc and realloc, which you guys should have already learned in class. So I'm going to go over a couple main use cases for malloc and dynamic memory allocation for starters. So let's say we have a scenario where I want to make a function. I'll keep a void for now. It takes in an integer and returns an array of values between 0 and n. So for example, if n is 3, I want it to return array for 0, 1, and 2. So the most straightforward way is you might be inclined to say, okay, well, we're in the function. Let's make an array first of size n. Perfect. Let's make a for loop and fill it with those values I was talking about. So I'm going to reset it for I, and then at the end we can simply return array. So we make this array right here, we fill it with values, and then we return it. Simple enough. And I got to check this return value. This is an integer array after all, so it should be an int pointer, not void. And then let's set n to 5 here, and let's call it. So it's going to be another int pointer, and we'll say function n, and we'll try to compile that. So you see when I compile it, I get this warning. It says function returns address of local variable. This might be a result of me turning on extended warnings. So if you do gcc, this is test.c-o test. Oh, I get even more. TD99. Oops, there we go. Okay, so I actually don't need to turn on extended warnings, but if you want to, you can do dash wall, and that will give me even more. Anyway, going back to our original error. So function returns address of a local variable. So we've already established that I'm trying to return an int pointer. So that's an int address. So it makes sense. This is telling me I'm returning an address of a local variable. Keyword here is local. So this is a local variable. It's defined within the function. Similarly, I is also a local variable that's defined inside this function. So it's telling me that I can't return the address of that. So why can't I return the address of that? Well, let's think about what the function's doing and what memory it's using as we go through the function. Apologies. So when I call the function to start, I pass in the n, I declare int array n. So this is an array of integers of size n. So this is going to return, or this is going to declare a block of memory that's big enough to fit n integers. Next, I do the same thing with I, except it's just one more integer. So more memory is declared just for this one integer. The program goes about its business, and then it tries to return this integer address. But then what happens to all that memory? Well, your function is not using it anymore, and these are all local variables, so all that memory disappears. So the I is gone, and the memory used for the array is gone. And what that means for us later on here is that the memory that we want to return from the function never gets to us. And keep in mind that this is different from when we want to return an integer. So let's actually say I had int k equals 5, and let's say I just wanted to return k as an integer. These are not the same thing. I'm not trying to return this block of memory. This block of memory gets copied over to the receiving variable. So if I had k over here, the value at k, so this 5 gets copied over to this k. The actual memory, though, is still destroyed once I leave that function. And we can't do something that simple with the arrays because we see this is just an address. The address does get moved over. So this is a number, again, specifying the address of this block of memory in your computer. So that address does get returned, that does get copied over, but the address doesn't point to anything anymore. There's nothing there because that's what got destroyed. So that's why we can't simply return an array. Well, how do we solve this with malloc? What we can do is, instead of declaring this array using the brackets, this bracket notation, this is going to put memory on the stack, which is automatically going to get destroyed as soon as we leave the function or the current stack frame. But what we can do is we can initialize this memory on the heap, and that's what malloc does. It'll initialize a block of memory on the heap, and heap memory doesn't go away until you explicitly tell it to go away. So let's think about let's go over the syntax for that. So again, I'm declare this as an int pointer, so it's a memory address. Even though I don't put the pointer here, when I declare it with these brackets, it's still an int pointer, but I'm not using the brackets anymore. So I got to declare it as an int pointer. And I'm going to set it equal to the return value of a malloc function call. And note, to use malloc, you need to include the standard library. So malloc takes a single argument, which is the number of bytes to allocate. So if I put 80 here, it would allocate 80 bytes. So that's 80 individual bytes, and it would return me the address of the first, that first byte. So if it allocates space for, I don't know, A, B, C, D, E, F, I would get the address of the A as a return value. Okay, but how many bytes do we want to allocate here? Well, I know I have an integer as the data type, and I want to allocate enough space for n of them. So it makes sense that I would want to allocate n times however big an integer is, or however many bytes an integer is. So we know an integer is not just one byte. So we can easily get how many bytes an integer is by using the size of function. And we can see that's built in, and I can do int. So this will be replaced with the number of bytes that an integer requires. And real quick, we can show that working. So if I just print size of int and go ahead and run it, we see I get a 4. So that means that an integer is 4 bytes. I can test out whatever data type I want here. We see a character is only a single byte. We can do double. Anyway, you can see that this clearly works for any data type. This also works for structures and custom types that we'll get into later. Okay, so now we know that a integer is 4 bytes. So we want to allocate enough space for n integers, so we end up allocating. If I put in 5 here, we know that size is 4, it's going to be times 5. This is going to allocate 20 bytes of space for me to use. And then we're going to go through that one at a time, just like we did with a previous array. We're going to go through it one at a time and set the value at each index equal to I. And a bit of a tangent here, but you might be thinking, well, if we allocate 20 bytes here, how can we still go through the array as just one at a time? Because we see I still go through it one step at a time, 1, 2, 3, 4, 5, but really we know that there's 20 bytes here. And similarly to when we have a statically allocated array, when we use this bracket notation, we're actually incrementing by the size of the element. So because array is an int pointer, your compiler knows it's an integer pointer. It knows it's an integer. So it knows when we put a 0 or a 1 here, we know we're actually offsetting that address by 1 times an integer. And again, we can, I want to highlight that really quick. If I take I'll make a quick array, and I'll make it static, and I'll set it equal to 1, 2, 3, 4, and then I will printf 2 values. I'll print out the address of array 1, and I'll print out the address of array 2. Go ahead and run that, and we can see that the addresses are 4 apart. So this whole big long number is the same up until the last one. First one ends in 2, the next one ends in 6. So we can see that those are 4 bytes apart. The first integer is at the 32 address, and the next integer starts at the 36 address. Okay, and I want to highlight that even just a little bit more. I already have this print bytes function here that's going to just print out the raw bytes for a block of memory. So I want to do print bytes. It takes the number of bytes. So I know I have 4 integers. So that's going to be 4 times size of int. So it should be 16. And then it takes the address cast as a jar. So we see I have, I'm printing out the memory addresses at each one of these, as well as the integer value or the, at each one of those locations. So we see I start at, we see my memory address going up one at a time, 0, 1, 2, 3, 4, 5, etc. And we see going up, I have 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0. So I have very small integers here, which is why they're not taking up more of this space. They're only taking up some of that first byte. But we see that this 1 actually is the 1, the 0, the 0, and the 0. So if I were to make this a very large number, I would start overflowing into those. And there we go. We can see I start overflowing into those further bytes. And again, this highlights another interesting thing. We see that they're actually going backwards. So as the memory addresses go up, the significance also goes up. So if we're thinking about how the 1 looks in memory, it doesn't look like this, and a larger number might look like this. It actually looks like this, and a larger number might look like this. So this is called the endianness of your system. So this is dependent on your operating system. And it varies. I know Windows are little endian. That means it starts at the smaller significance and gets higher. The other way around is called big endian, but it depends on your system, and it's just a bit of a tangent. Okay, so going back to our function with malloc. So I have this malloc call. I've allocated n times size of integer amount of bytes, and I've set array equal to the pointer. One thing we can't forget is that malloc will actually return a void pointer. So that's this data type. This is the data type that gets returned, but I have an int pointer here. So I want to explicitly cast it as an int pointer, saying, hey, this address is an integer address, not something else, because that's important when we go to index it, as we have already discussed. All right, and then let's get our function back. We can see when I compile that, I get no errors. And then if I want to print some of these values, so let's just print out some of these. And by some of them, I mean all of them. And there we go. I get my 0, 1, 2, 3. So even if you were to do it the other way, you might still get these results, but this is a safe way of doing it where you know that this memory, the memory that you allocate here, will never disappear until you explicitly tell the computer, I don't need this anymore. So, and to do that, we use the free function, and we just pass in the pointer that we allocated into the free function, and that will tell your operating system, I don't need this memory anymore. If you don't do this, if you don't use free on your memory, and you somehow lose the pointer to this block of memory, that's called a memory leak. So you might have some programs where if you open up the task manager and you just watch it for a while, you can see its used memory just keeps going up and up and up and up and up. And then you close it and reopen it, and suddenly, okay, now it's running smoothly again. That happens because those programs might have some unintentional memory leak where they're accidentally losing the handle to this block of memory. So if you think of this address as a handle to this block of memory, if you lose that handle, then you're no longer able to call the free function on it. So your operating system will never give it up, and it will just keep that memory that you're using just going to keep piling up and up and up as you use the program. So we want to avoid those. So just like opening and closing a file, every time you malloc a block of memory, make sure you have an accompanying free. And you need to make sure that that's every single call to malloc has an accompanying call to free. So for example, if I were to do this, well, I wouldn't want to declare it again. If I were to overwrite this immediate pointer with another call to malloc, this is a instantly leaking memory because I no longer have a handle to this block of memory. There's no way for me to get it back. It's gone. My program will always have this memory allocated until the program closes. So I know sometimes in a lot of years, people get kind of stressed like, oh, I ran my program and I forgot to call free. Does that mean the memory is always going to be allocated? No, when your program closes, it gets freed anyway. All the memory associated to your program gets destroyed by your operating system anyway, so you don't have to sweat not calling free for your sorry your programs. But for it's best to make sure you're calling them. Again, we're trying to practice good coding here. So if you have it doesn't really make a difference on these small programs, but if you have a huge programs, these do make a difference. Okay, so moving on to the next big kind of, the next big use of malloc, and that's dynamic array sizing. So we already kind of saw that there. We have an array of size n, and that's dynamic because we don't really know the size of n, but what about an array that changes size? So we know that if we allocate an array like this, so int array something, we have to put something here. We have to put some kind of number here. How big is it going to be? Well, if I put a 5 here, if I want 6 elements, if I decide later on that I want 6 elements, how can I get 6 elements here? Well, you can't. You cannot. So the only way to do it is you would allocate 6. You'd copy the memory over from array, this, I'll say array 1 and 2. You'd copy the memory from array 1 into array 2, and then you would destroy array 1. And that's actually exactly what the realloc function does. Realloc, except it works on dynamically allocated memory. So let's say I will actually remove these, and I'll say while, here, I'll do this. I'll make a for loop. I'll have my for loop run 5 times, and each time I'm going to append an integer to an array. So I'm going to start off by making an array, and every single time I run this for loop, I want to add I as an element to array. So I should have array I equals I here, but array doesn't have any. I'm going to start off array with no size. To do that, I'm going to set it equal to null to begin with. This needs to be done. If you intend to use realloc to resize this array with null, you need to set it equal to null. So passing a null pointer, this is called a null pointer, into realloc is just fine, but passing garbage into realloc is not fine, and it's going to get you very confusing errors, and it's not going to tell you that's the problem. Similarly with free, if you call free on a null pointer, this is just fine. Nothing happens, nothing bad happens. But if you call free on an uninitialized pointer, it'll give you more cryptic errors. Usually your program just crashes, doesn't say anything, just stops functioning, and you'll be left to kind of hunt down these errors. Okay, so I start my array with no size. There's no elements here. So I know because I want to add add I as an element to the array, I need to add a spot for it. So I can do that by using the realloc function. To do that, realloc, similarly to malloc, returns a pointer. So I also want to explicitly cast it as an integer, as I did with malloc. The first argument to realloc is the memory address to reallocate. So I'm going to choose array. This is the address that I want to make bigger, we'll say. So right now it's a null pointer, but as I just mentioned, this is totally fine. Realloc doesn't necessarily need an initial address to have memory in it to reallocate it. It's totally fine starting out as null. The next argument is how much space to allocate. So right now I have 0 space, but I want to put 1 integer in there. So on the first iteration, I want 1. But again, on the next iteration, I want another integer. So I'd want 2. And then next, I'd want 3. So I can see pretty quickly that really I want I plus 1 integers. But similarly, realloc is taking the amount of space in bytes. So it's not the amount of integers I want. It's size of integer times the number of integers I want. This is how many bytes to allocate. Okay, after I reallocate it, I set the spot. So this is on the first iteration, this is going to allocate 4 bytes to me, or 1 integer. I'm going to immediately assign that integer to I and then move on. So at the end, if I want to, I'll just have a quick print statement. And I'll print array at index I. That. And we say I get an array that's 0, 1, 2, 3, 4, exactly like I wanted, even though I started with an array of size 0. Now, needless to say, this is kind of a trivial example. I know exactly how many integers I want to have in the array, so it makes much more sense to, if I'm not going to allocate it like this, it at least makes more sense to only have one call to malloc right there, and I can just hard code a 5 in right there. But this is more just to highlight the fact that you can make more space in your array if needed. Another interesting note, though, is the address that gets returned from realloc, we see I have to overwrite array, is not going to be necessarily the same. It probably will be the same depending on how you realloc things. Like in this scenario, the address of array is probably always the same after I initially set it off of null, of course, but it's not necessarily. So if I initially, if I declare, I say I need 20 bytes, I need a 20 byte block, and your operating system will give you that 20 bytes, but then somewhere else in your program, you say, I need 20 more bytes. Or sure, I should say I need a different 20 bytes. Okay, those 20 bytes are going to be allocated probably right after the first 20. You can't just go back and say, that first 20, I actually want 30 because there's no room for it anymore. That second batch of 20 values, that second batch of 20 bytes is right next to the original batch. So I can't just add 10 more onto the original. That space is already taken and accounted for. So in that scenario, realloc would probably allocate 30 bytes after that second batch of 20, and you'd end up with just empty space where the original 20 bytes was. Another note about realloc. So it will free the initial pointer. So in that circumstance where the pointer's changed, it will free that initial block of memory. It is reallocating it. So it allocates a new block, it copies over the information, and then frees the original. So we don't have to call free every single time we call realloc. Realloc is calling free under the hood for us. But what we do have to do is, just like malloc, we need to make sure we free the final block. So whatever final value realloc gets from this for loop, we need to make sure that that's freed at the end of our program too. All right, this should give you guys plenty of ideas on how to approach the lab with the moving or shifting array sizes. Should give you a good introduction to malloc and realloc. There are other allocation functions like calloc, for example, is another one, but we won't get into that for this week. So with that, wish you guys good luck.